Let's look at some of the finer details of acid-base reactions. First of all, really quick definitions of what acids and bases are. The first one is probably one that is the most familiar, and the one that is unfortunately the most primitive. It's called the Arrhenius model. This is the same Arrhenius who helped us figure things out about electrolytic behavior. But basically, when they're talking about acids and bases, they define them, first of all, by dissolving them. So when acids dissolve, they produce H plus ions. Meaning, when they dissolve, somehow, some way, there are more H plus ions in solution as a result. On the other hand, bases, when they dissolve, they also produce something, but in this case, it's sort of its counterpart, OH minus ion. But kind of a more general definition, one that ends up being more broadly applicable, is not limited to just things that are dissolved, is our friend Bronsted-Lowry. So in this case, the Bronsted-Lowry model takes an acid and defines it as something that's considered a proton donor. So the word proton, which we're going to kind of get into right here, H plus ion is really a proton. Well, why is that? Well, again, if you think about a hydrogen atoms just have one proton and one electron. And so when you become an H plus ion, electron goes away, so you're left with just a proton. Right? It's an H plus ion, it's just a proton. So we consider that again to be the thing that's being donated here. And an acid, therefore, is a proton donor, whereas a base is a proton acceptor. Also notice how the base doesn't involve hydroxide anymore, right? So OH minus isn't necessarily a guaranteed substance that we're working with in the Bronsted-Lowry model. This ends up being a little bit more broadly applicable, and that's why the Arrhenius model is kind of a simplistic one that we can maybe use as a basis, but then we'll really need to look at how this is more of a proton transfer. A bit of a reminder, here's some strong acids and strong bases, because how we write them out and such becomes important. Here's a quick review. The chemical equation, write the chemical equation for hydrobromic acid, being dissolved in water. Hydrochloric acid, hydrobromic, said the wrong thing. HBr, that's being dissolved in water. It's a strong acid, right? So being strong, we know it's going to separate completely. So in this way, we result in the ions like that. Whereas hydrofluoric acid, we recognize, first of all, that's HF, that's dissolved. But because it is a weak acid, we know that only partially dissociates, and we represent that with an equilibrium, meaning it's going to go back and forth between H plus and F minus ions to go back and make HF. At the same time, HF will separate into H plus and F minus. What about bases in solution? So in this case, writing the chemical equation for barium hydroxide BaO2 ends up being one of the strong bases. So we know that completely separates into all of its ions, and you have two hydroxides. Whereas for ammonia, ammonia is the formula NH3. It's a base composed of mostly N's and H's. Let me write that down here. Okay, and that ends up being NH3. But this is one of the rare ones, NH3. Not rare ones at least, but when it comes to weak bases, the type that we'll work with, this is one that actually requires water, because water ends up getting affected by this. And also it's an equilibrium to make NH4 plus AQ and hydroxide. Okay, now let's keep going with how we describe these acid-base reactions. First of all, instead of just saying acid-base, sometimes we'll just say neutralizations instead. So these neutralization reactions, we can assume that there's some acid and some base involved. And very often, it actually kind of looks like precipitation reactions, meaning whenever we talk about these acids and bases, there's some sort of background assumption that they're probably going to either behave like ions, where they separate out into their ions and then they swap. And so we can basically expect that these kind of follow a very similar pattern to what we've seen in the past when it comes to precipitation reactions. Same idea, right? Which suggested products are likely to occur, which ones are not. And again, that's something we'll have to use and kind of sort of work through as we look at these. Very often, again, we can actually see this more accurately as an acid-base reaction, where it's more about proton exchanges as opposed to H plus and OH minuses coming together. That will help make this a little bit easier for you. And we'll look at some examples in a minute. Just to be clear, right, this language right here, acids will donate the proton that the base accepts. If you remember, this is basically effectively how the Bronsted-Lowry definition was stated as earlier. Instead of thinking of a bunch of H's and OH minuses, really it's about following the path of that H plus ion. Let's go and take a look at some examples here. First of all, sodium hydroxide and hydrochloric acid. These are solutions that are going to be mixed. Sodium hydroxide we know is a strong base. We knew that from before. Hydrochloric acid is a strong acid. So basically mix them together and see what happens. So sodium hydroxide, let's try a better O there. Sodium hydroxide, that's in solution. And hydrochloric acid, that's also in solution. Will be mixed together and produce some ions. So what goes on here, right, is that you have NaOH, you have HCl. You can kind of almost imagine the NaOH there, HCl there, kind of basically doing its thing where it separates out in solution. And then we want to swap ions. So what do you get as a result? You get our friend H2O, which is a liquid, right? It's not dissolved in water. And then the Na and Cl that then combine to form sodium chloride as a potential other product. Now, as a net ionic equation, right? This one we just look at the parts that really matter, the parts that really change. Well, what do we know about the idea here is that if it makes something new, that's going to be kept around. But if it makes something that's still dissolved in water, like NaCl aqueous, remember this has a strong electrolyte. Na and Cl wouldn't actually come together, right? These are still free-floating ions that hang out in the background. And so ultimately, it's basically looking at whatever makes H2O. So in this case, it'll be OH minus and the H plus ion that forms water. Now, whether or not you believe it, right? We talked about this in the previous slide, how if you look at the last bit here, we're talking about acid-base reactions being more about proton exchanges. So in a certain way, right, you kind of almost have the H plus kind of transferring itself to OH minus to then form water. And so kind of keep that in the back of your mind. This one's not as obvious, but that's effectively how it works. Let's try another example. Strong acid, strong base. So this time, again, nitric acid, calcium hydroxide. I think you kind of recognize these names, HNO3. Calcium hydroxide, CaOH2. Go ahead and try to make these happen. So combine these, write a balanced equation, and then of course write the net ionic equation with it. So what a weak acid, strong base. So in this case, the acetic acid is treated with sodium hydroxide. So in this case, acetic acid is the formula H2H3O2, and it's considered a weak acid, right? Because it's not one of the strong acids. And then, strong acid. The sodium hydroxide, of course, is classic base there. It's going to be a strong base. A couple of things to consider. Most of the acetic acid exists unionized. That's not unionized, but unionized in solution. That's because we know it's a weak substance, so only very few particles, again, comparatively, we're talking about like, maybe 2% or so. 2% of all the particles of acetic acid separate into their ions. So 98% of them, most of them, are unionized. They're still their complete C2H3O2. So in this case, what we're kind of doing is almost imagining the hydroxide ions from sodium hydroxide are basically removing hydrogen ions attached to the acetate ion. Now, this idea of removing hydrogen ions, this is basically an alternate way of thinking about how H plus ions are being donated, right? So we're transferring it from the acid to the base. All right, we'll see this in action here. It makes a little bit more sense when we write the chemical equations up. So HC2H3O2, that's aqueous plus sodium hydroxide. That's also aqueous. And let's see what the products are going to be. If we have this, again, it's kind of swapping, if you can imagine that, right? We're going to form water and sodium acetate. All right. Now, the next question here is, what does the net ionic equation look like? So here's where we kind of have to do a little bit of, not necessarily finagling, but I kind of have to consider the realities here. What's going on in solution is, like we said earlier, all of this, like 98% of it, most of it, is still together. So I don't really expect it to separate out. So really, when you have this dissolved in water, we kind of view it as, a held together substance. On the other hand, you have NaOH, which we know is a strong base, right? So this one's going to completely separate into sodium and hydroxide. Same thing with this product over here, NaC2H. So these two, again, are going to be separated because it's also a strong electrolyte. Remember, the sodium is a alkali metal. Anything combined with sodium will always be dissolvable, and ionic compounds that are soluble in water will always separate into the component ions. So ultimately, your Na ends up being something that we call our spectator ion. Remember this, right? Spectator ion. Whereas everything else over here isn't necessarily, because this doesn't actually, again, separate that much. So most of it stays together. So the result is, really, we actually kind of keep all of this. It's a little bit unusual because previously we kind of just got rid of anything that didn't seem like it made a difference. And we keep all of it. And then we do keep the hydroxide ion over here. All right. Spectator ions we ignored. They don't change in this reaction. they're kind of always in the background hanging out as spectator ions, not really being involved. So we kind of disregard that part, but we keep everything else. And so it's going to look more like this. All right. So again, same idea here, the sodium and sodium on both sides. These are both spectator ions. They haven't changed in this reaction, but what has changed is that, again, most of this, right, is still together as one substance. And the hydroxide effectively receives the H plus ion to then make water. And as a result, the ion of acetate is left over, and we represent that in the net ionic equation. So these aren't nearly as simple as just, H plus and OH minus making water. This one involves a little bit more because we involve a weak substance. In this case, let's go and try it out now in the other way. We have a strong acid or a weak base, so ammonia, classics, a weak base there mixed with a solution of hydrobromic acid, which again is a strong acid. So what's the balanced equation? Let's try this out. HBr, AQ, and NH3, AQ. It's going to form H2O. Whoa, hang on now. All right, so normally we can just go ahead and race right through and say it's going to make water and then something else. But this one, oh man, this is a little bit more complicated. But you have to remember, right, we kind of like to think of this not as a bunch of H's and OH's, but rather about transferring, right? So looking back at that Bronsted-Lowry definition of transferring protons. So HBr acts as our acid, and so as an acid, this H will be expected to transfer from here to here. And so as a result, what should we really get is we should be getting NH4 plus AQ and Br minus AQ. It's kind of a strange idea here, right? Because again, we're seemingly changing so much about this to where it looks like that you're all of a sudden having these brand new ideas. And ultimately, if you really want to, you can even write this as NH4 and then Br AQ, right? Because ultimately, we're moving that over here. But then, of course, because they're positive, negative ions, we don't really write out separate ions in a balanced equation, right? We write it out as a single thing. So ultimately, right, this is going to take like 3 different steps to be able to get from the original prompt to this one right here. Now, finally, the net ionic equation. Well, again, remember that things that separate out, right? So the bromine, or the bromide anyway, in this case, when it's dissolved, this is all separated. The bromide over here, again, these are all very soluble substances. It's an ionic compound that dissolves in water, so they're completely separated. The bromide also ends up being a spectator ion for this example. So a spectator ion for the bromide, spectator ion for the bromide. So ultimately, in this problem, to write the net ionic equation, it becomes H plus AQ plus NH3 AQ makes NH4 plus AQ. All right, this is kind of a strange one, but effectively it still follows the same principles of what we know. It still has about proton transfer, and then we end up having what, for a net ionic equation, we kind of disregard the spectator ions. All right, here's some examples of practice. Go and try these out. Definitely a bunch of them to consider, and they more or less follow the same principles. It also does say if you can do net ionic equations, go ahead and do it, and then there you go. Practice 2, again, same idea. Go ahead and putting these together, and then you'll be able to put some acid-base concepts into this one. Finally, let's go ahead and address some acid-base stoichiometry. As you can imagine, anytime we deal with solutions, we always have some way to quantify the mole amounts in various volumes. So this is the same idea. Right, so in this case, the question is asking what volume in milliliters of a 0.10 molar HCl solution is needed to neutralize 25.0 milliliters of this solution. Okay, so let's try out a couple things here. First of all, we have to work through this as we would for any stoichiometry problem. So as always, we have to have a balanced chemical equation. Let me slap that on here real quick, and there we go. Now, as always, we're doing stoichiometry. We're talking about reactions. That means we have to have some quantities around. So far, we don't have anything yet that's actually usable, but we're gonna have to do a little bit of work, right? Normally, if we have grams, or normally if we have, moles, it's some little bit of processing we have to do. In this case, right, we got to get to where moles are going to be the most useful, because as always with stoichiometry, we got to find some mole ratios to relate different substances. All right, let's try this out. I'm going to go ahead and take the information provided by the 25 milliliters. And this right here, I'm going to do a little bit of shorthanded work here. I'm going to kind of assume you can know what to do with a volume and a molarity, right? Remember, you use the molarity formula. So the mole amount as a result of NaOH, that's going to equal 0.00875 moles of the base. So we have the sum amount of the sodium hydroxide. the language is saying how much of the HCl do we need to neutralize that? Well, again, I gotta figure out a volume here. I only have a mole amount of this. Well, if you remember, right, when we talk about neutralizing something, we're effectively finding a stoichiometric ratio. I mean, we're finding that perfect amount of one substance so that it completely reacts with the other substance, right? No excess reagents. Both of them are considered limiting reagents. And so in that case, what are we basically doing is doing a little bit of quick stoichiometry using the mole ratios. So in this case, it would be 0.00875 moles of NaOH. Using some stoichiometry, doing some relationship between the mole amount of NaOH and what perfect amount of HCl would it take. Well, again, thankfully, it's a 1-to-1 mole ratio, so it's pretty quick to show the work to do HCl. And so that means you're also going to need 0.00875 moles of HCl in order to completely neutralize 0.00875 moles of NaOH. But of course, finally, the question is not asking for a mole amount. The question is asking you about the volume of the solution of HCl. So again, I'm going to apply the molarity formula. Again, I'm going to count on you to do some sort of conversions between milliliters and liters. And your final answer there for HCl would be 87.5 milliliters. Last problem here, this one's going to be very similar, but if you notice, in this case, you're given, right, the typical acid and base again. But notice you're given amounts of each reactant. So when that happens, typically there's a little bit of limiting reagent involved. So go ahead and give this a shot as well, and then work through this one to figure out the answers there presented at the bottom. All right, that'll do it.